So my talk today is about comprehensive aerial survey in the New Mexico Permian Basin, which reveals missing super-emitters. So this work is jointly done by Professor Adam Grant's group at Stanford University, as well as Kairos Aerospace. A bit of introduction of myself. I'm a PhD student at Grant's lab. This talk was given a 10-minute version yesterday at EPA's GHGI workshop, and I hope today's 40-minute version would include many more details and content. So quickly about Kairos technology, Kairos Aerospace has this hyperspectral sensor that can be mounted on an airplane that's flown at about 3,000 feet or 900 meters. And their end product would be an optical map that's overlaid with the methane plumes detected. And they also report the quantification results of those methane plumes. So to verify this technology, we did a control release testing in a single blind fashion in Stockton, California here over the course of 5 days in October 2019. In total, we collected over 200 data points ranging from the release rate of 18 to over a ton, 18 kilogram per hour to over a 10 kilogram per hour, which is over 10 times of the size from other control release studies, and making this the most appropriate for assessing the performance for quantifying super-emitters. And the results looks good. The technology shows good fit for all of the release ranges that was tested. And notably, a lot of this error is from the uncertainties of wind analysis, reanalysis products, rather from the hyperspectral sensor itself. So if we replace the this is called high resolution rapid refresh wind products from NOAA. With a ground measured wind, our R square would go up from 0.67 to 0.8 to over 0.8. And control release testing also shows that the 50% detection probability occurs at about 10 kilogram hour per meter per second wind. This term is reported in a wind normalized term because the stronger the wind blows, the more dissipated the plume would be, and the harder it is for us to detect the plume. So the way to read into this number is that, for example, at 3 meter per second wind, we will see a 30 kilogram per hour of plume about half of the time for this technology. So this technology was deployed in the New Mexico Permian Basin, so this area that's shown on the map. And the way that Kairos covered this area is as follows. They will first have a predetermined polygon and fly to cover one stripe of this polygon, and then they would turn the flight around so that the plane around so that and a partially overlapping stripe can be covered. In this way, this asset A and asset P in this overlapping region will be covered twice on that day. And Kairos would then turn the plane around once again until the entire polygon is covered. So in total, this is the asset that was covered in the study area and colored by the number of site visits on the log scale. And this area is over 35,000 square kilometers with over 30,000 wells. And Kairos covered over 90% of them, which is why we have in the title slide that we call this a comprehensive survey. And this area has also over 15,000 kilometers of pipelines, including gas stream pipelines. Now, this was done on 115 flight days. So each well or each point source here were covered on an average of 4 times. And that gives us a totaling of over 17,000 well visits in this area. The detections or the coverage speed is about 1,000 wells per day. And this is what we found, about 2,000 plumes from 1,000 emission sources due to repeated coverages. So in order to derive the basin area total emissions from this survey data, we first took our plume level quantification results as well as the wind associated with those plumes. And we calibrate the rate based on the control releases. I would like to note that for our base case, we choose a sublinear fit to stay a bit conservative and to better represent this data spread. And the next step would be selecting one plume for each emission source and also account for intermittency. One example shown here is that if a single source was observed 3 times during the survey, and with observations 100, 0, and 200 kilogram per hour, then we would compute a persistence level of 2 SIRs for that source, and also a persistence average source size to be 100, which is 300 over 3. And we do this in a Monte Carlo fashion. So the mean would be 100, but we would randomly select one from these 3 observations to be the emission source, to be the emission rate of that particular source. Once we sum these emission source level rates up, we will get our directly measured emissions. Now there are also sources or other things that has not been detected. So one thing that we account for is the undetected emissions that's within the partial detection range. And the way we do this is to take this chart and, for example, from the 12 to 14 range, Kairos was able to detect 20 out of the 22 country releases data points. So what we do is essentially filling this bar to the top. So we would, if about 22 plumes if 20 of such plumes were detected in the field, then we would add 2 additional to this to fill this to the top. And we do this for every bar here to account for emissions that's within the partial detection range. And we also extrapolate to all assets in the survey area. That's essentially by dividing the 90.4% coverage rate and assuming that what is not covered exhibits the same emission performance as the assets that were covered. The last step will be accounting for things that's under the detection limits, the minimum detection limit. And let me elaborate a little bit on that. So because we don't have any data for what was actually below the minimum detection limit, what we could do is assume a national average loss and also a national average site level distribution of emissions here. And the way we do this is to take the 1009 site level emissions from a synthesized data set from O'Mara et al. This is a national data set pulled from multiple surveys. And we also pulled some HRR wind for our New Mexico sites. And once we divide that, we will get a wind normalized or wind independent methane rate by dividing the methane emissions from the O'Mara sites with the New Mexico wind. And let's assume that we can simulate a Kairos overflights over these assets. And above the Kairos minimum detection limit of 2 kg/h per meter per second of wind, this is what could be detected by Kairos, and that's only 79 out of the 1009 sites. So about 8% of the sites could be detected. However, due to the habitat distribution in this O'Mara data set, that 8% of the sites account for 63% of total emissions, meaning that only the rest of 37% of emissions cannot be detected by Kairos. And so we would just multiply this undetected volumetric fraction with the Alvarez et al. Estimated national total loss to derive an additional loss rate of 0.8% to be below Kairos minimum detection. So this step would be just adding 0.8% multiplied with the production in this area to get our survey area total emissions. So this is our result. As expected, we found a lot of emissions, over 150 tons per hour, just as the directly measured emissions. And our extrapolation doesn't add that much, but our total is substantially 194 tons per hour, which corresponds to about 9%, over 9% of gas production in this region. And as a comparison, EPA's national average estimates would be 25 tons per hour for this region. And we also account for the production growth across the 2 study periods by adding 5 tons per hour to it. Regardless, the 2 estimates are still drastically different. with 5.1 to 7.5 times difference here. And we see that the 9.4% is a really huge number, and so we did a bunch of sensitivity tests to try to get some idea around the uncertainties here. So going from the base case, which is use the sublinear fit for calibration, we also tried a linear fit, and expectedly the number would go up a little bit, however, not too much deviation. And we also think maybe wind is a big error source here, so we tried a different source of wind, namely dark sky. And interestingly, the two dark sky retrievals in February 2020, October 2020 give us different results. However, the number still stays around the range of 8 to 10%. And we tried 3 additional cases, which does not make sense. They're just for conservative tests. The first one we tried is disabling extrapolation to assets that was not covered. So that's assuming whatever has not been covered has 0 emissions, and that will bring the number down to 8.1%, but that's still above 8%, which is still huge. And what if we exclude everything that's below minimum detection? That's essentially taking the 0.8% that we just computed from the 9.4% base case, which give us 8.5%. And what if the top 20 plumes, or about top 1% of plumes, are all outliers? They're all just really huge, and that those could not happen, then the number will still stay above 8%. So, what could cause these discrepancies? Here are several reasons that we can think of for explaining the difference between ground surveys and the aerial survey. Firstly, ground surveys, on which the GHGIS heavily rely on, may overlook certain emission source types, such as tanks, inlet flares, and gathering lines. Well, I got a comment yesterday that ground surveys do not overlook tanks, but however, there's still the categorical issue of whether you count those intentional tank pressure reliefs as fugitive emissions, or are they just operational and should not be counted towards the total emissions. And secondly, for ground surveys, operator consent for access is usually required, and which may cause bias. And thirdly, which is one important reason that we want to talk about, is that the limited sample size for ground surveys may not fully capture these super-emitting events, which have low chance of occurring but high consequences. And this is possible that maybe those quantification technologies used in ground surveys, for example, OTM-33A and high flow sampler, are not designed for the size of aerially detected super-emitters that's on the order of 1 ton per hour or larger. And we don't have enough data to support this, but we hope that the New Mexico Permian is leakier than US average due to its limited gas takeaway capacities. So let's first take a look at the first reason, the overlooked emission source categories. This is work done by Rutherford et al. Who's also in our group, and he reproduced the EPA GHGI using an updated set of component level emission factors, and found that tank emissions might be largely undercounted in the GHGI, as well as equipment leaks. And additionally, this is an inlet flare footage of infrared footage that was found in the Texas part of the Permian just this year, and these anomalous sources are also underrepresented in current ground surveys. And our results also shows that if we break our 153 ton per hour directly measured emissions down by their source types, then we found that about half of the emissions come from the well sites, and the rest come from midstream assets, and most significantly pipelines and compressor stations. By the way, let me clarify. So by a well site, we refer to everything that's on the well site, including the wellheads, the storage tanks, sometimes compressors, and also the gathering lines that's on the well site. And if we refer to a site as a compressor station site, then this site can contain storage tanks and pipelines, but cannot contain a well or a gas processing plant. And the storage tank site can only contain pipeline, but it's not compressors or wells. So as shown on this graph on the right here, the x-axis are all on the log scale. So all of these source types exhibits very heavy tail distributions, and a large part of it are the leaky midstream contribution. If we take a look at the cumulative measured emissions and plot that against the persistence average methane emissions, then we get that the distribution is also very heavy-tailed as expected. The top 10 emission sources here includes 5 well sites, and 2 of which look like inlet flares. One really large source is a pipeline, it's a gathering pipeline. And there's also one really large tank site that's over 1 ton per hour. And 3 compressor station sites are also among the largest ones. And these top 10 sources alone account for over 10% of total emissions that we found. And if we compare this against other ground surveys, 287 kilogram per hour is the largest source that's found in the Omar et al. Synthesized data set. And as we can see, over 50% of total aerially detected emissions are from a persistence average source larger than the largest ground detected source. So let's look at this in a bit different way. So this plots the DSL and 90 Omar et al. Sizes with the aerial detected sources. And please note that in this simulation, I'm not taking into account of the null observations. So in that example of 100, 0, and 200 observations from a single site, the persistence average will take into account that 0 observations, so the average will be just 100. But in here, because this is in our multi-color iterations, I don't take into account those null observations. So this number would just be either 100 or 200 from that example. And the 2 distributions barely touches, although they both show that they are both heavily tailed. And if we plot this against the cumulative emission fraction, then we see that if we don't take into account null observations, then 80% of the total aerial detected emissions are from sources larger than the largest ground detected source. So this gives us a question of how could this happen, and one very possible reason that we can think of is sample size. Let's suppose that we have a very heavy tail distribution, and we know that the ground truth is 1,100 kilogram per hour for this population, which includes 100 small leaks at 1 kilogram per hour and 1 huge leak that's at 1 ton per hour. So there are several ways that we can sample from this heavy tail distribution. The strategy number 1, which is sample the entire population with a device of sensitivity less than 1 kilogram per hour. This way, we will find all 101 of these leaks, and we don't need to do any extrapolation to know that the population total is 1,100. And strategy number 2 is the natural deviation from strategy number 1, because this is prohibitively expensive to do population level survey, ground level for over 1 million wells in the US. So strategy number 2 will be sampling a subset, for example, 5 leaks from these 101 population. And the result will be that 95% of the time, only the small leaks will enter the sample, and our extrapolated total is just 101 kilogram per hour, which is less than 10% of the actual total. And only 5% of the time, our extrapolated total will be huge because this super-emitter enters the sample. Now, please note that this estimate is actually unbiased, because if we multiply 95% by 101 and 5% by 20,000 and add those up, we still get 1,100. However, in real world applications, it's very likely that we enter in this 95% universe. And even at times when we enter into this 5% universe, there are reasons to believe that 1,000 kilogram per hour sample could sometimes be discarded. And strategy number 3, which is the aerial screening strategy, would be sampling the entire population, but with the device of sensitivity over 1 kilogram per hour. This way, we can only detect this huge source, and our total would be 1,000 kilogram per hour. And we need to make assumptions for what's below the detection limit. However, the takeaway message from this slide is that we think it's better to be roughly correct than precisely wrong when we are facing a heavy tail distribution problem. So reflecting this on our observation, what if we only made 100 well visits rather than 117,000 well visits? This graph here shows the cumulative probability plotted against the fraction of measured total well sites after scaling up. So this is the mean, which equal to 1 of our emissions. And we did a random sampling of our 117 observations, and this is how the things will look like if we sample randomly from those 117 well observations 117 times with sampling with replacement. And what if we only do 100 well visits? This is what it looks like. So about 38% of the time, none of the 2,000 plumes observations would enter into the sample, so that the extrapolated total would be just 0. And about 72% of the time, we will arrive at the underestimation of the actual total compared to the results from the over 100,000 visits. Even when we increase the sample size to over to 1,000 or 10,000, our sample total will still be have a pretty widespread here, with a significant chance of arriving at estimates that's that's over 50% different. So this is why we think population survey is key for sampling from a heavy tail distribution. And to do a very short conclusion of what was covered, we think aerial survey unveils more super-emitters and leaky midstream infrastructure, which is why we found very high emissions in the New Mexico Permian Basin. And note that these emissions from just 1,000 sources account for the vast majority of total emissions. So we detect the vast majority, and whatever it has in our extrapolated portion is smaller compared to what was detected. And midstreams, the compressor stations and gathering lines are also substantial sources that might have been overlooked. And we think population survey is key for sampling from a heavy tail distribution, and this should be incorporated in future emission accountings as well as leak detection and repairs. So that was for the comparison with a ground survey. So how does this study compare with other aerial studies? This is an aerial study that's done by Zhang et al., and they used the TROPOMI data, satellite data, and applied inverse modeling techniques to this area of Permian, which spans both New Mexico and Texas. And they used the EPA's GHGI as their prior and TROPOMI observation as the observation, and generates this posterior estimates for total emissions in this area. So how do their results compare to ours? The blue area here is their reported Permian average for this region. And we did a bunch of alignments. Let me specify what they are. So their base case would be 64 ton per hour for this region. And if we do a spatial alignment, namely restricting to their posterior in this region, in the New Mexico Permian region that overlaps with our study area, then we see an increase in average, so that our number would go up by 15 ton per hour. And if it's GHGI, because it's roughly, there's less variance in this region, and the GHGI wouldn't change much. And what if we, well, there's another set of alignment that we did, which is the study period alignment, to account for the production growth that's between the two study periods. and that adds another 14 ton per hour to the estimate. And the third one is the time of day alignment, which adds an additional 13. And let me show you a graph on that to see what I mean. We found that morning to be leakier than afternoons according to ground surveys. According to our aerial survey. So here on the top here, the red shows the number of point sources. The number of plumes that was detected in each hour. And the gray here shows the number of point assets that was covered in each hour. So if we divide the red by the gray, that's how we get to this graph B below. So the division would give us this fraction of leaky assets at each hour. And we found that, there's less coverage records in the morning. That's why the error bars are larger here. And we found that in the afternoon, tends to be less leakier on an incidence basis. TROPOMI overhead time here is constantly 1:30 p.m. local time. So that means that about 14%, at this hour, the total incidence based leaking rate is about 14% less than the average that's covered by Kairos. That's why we did this alignment here and bring the estimate up a little bit. And now that we see the two error bars here touches, but there's still this remaining divergence, and what could be causing that? There are several reasons that we can think of. First, that it's explicitly written in their manuscript that there's some unexplained enhancements in the northwest region of this area. So this part of the enhancement might have actually been caused by oil and gas operations in the production region. However, it's not accounted for. And secondly, their methods use a pretty conservative prior, which we know as the EPH-HGI, and that may bias the total low also. One way that we are trying to collaborate with this team is to, instead of using the GHGI as the prior, maybe use what we can generate as the prior. And that give us the conclusion of that high emissions is being observed in New Mexico Permian by both aerial and satellite studies, and constant overhead time of satellites may cause some bias in final estimates. And as a next step, maybe use the aerial's bottom-up studies to generate alternative players for satellites top-down studies.